it off?
Yeah. Yeah, you have to take those things. Right here. All right.
I'll fix it with dirty.
All right. I have to repeat everything I just said. So, all right. My name is David Hines. I'm in charge of the electron microscope here down at Mount Hope. The electron microscopes, there's only this one besides Carreri, this is the only microscopes here in Trinidad. In the region, actually, there's one in Jamaica and there's one in Guadeloupe. In Jamaica, I don't think it's working, but those are the only microscopes around. Let's start with the basics. This is a light microscope in which this is your sample. Light hits the sample, it comes through the lenses, and you see it with your eyes. Basic theory. This same principle with the electron microscope. You have an electron beam that's being generated, goes through the chamber, which is controlled by a magnetic field, hits the sample, and goes out to the detector. The difference is that this one has lenses and glass. This doesn't have any lenses, glass, or anything like that. And it's not light, it's actually electrons. It's being pulled off the filament. This is the filament. It's a tungsten filament, and this is, you can pass it around if you want. That little wire is where we, huh? Okay, all right.
Thank you.
Okay. The tungsten material, the electrons are being pulled off the tungsten material, and that's what generates the electron beam. We have one detector that detects the image, and one detector that detects, is an EDS detector, which is an energy dispersive system, which can tell you materials. Now, the two electron microscopes here, there's a scanning electron microscope and the transmission electron microscope. Scanning electron microscope looks at surfaces. Transmission electron microscope looks through the sample. It's transmitted through the sample. So, this microscope itself goes up to 30,000 volts and a magnification of 169,000 times. They can go all the way up to 300, 400,000 times on the microscope. So what could you see with that? You could see actually bacteria, viruses, insects, whatever. So let me show you what's going on in here. Oh, everything in the microscope is under vacuum, high pressure vacuum. So what you hear going on there, that's the rotary prop, which goes from atmosphere to 10⁻³ torr, and then it goes off to the diffusion pump, which goes from 10⁻³ to 10⁻⁶ torr in vacuum. Reason for the vacuum is for the filament. The filament works just like a light bulb, like if you know how the light bulb works, it's under vacuum. It has a tungsten in there, it's being heated, and it's 112% material. So here is where your sample goes. These are just translations you will be moving around. Let me show you. This is where that filament sits, and it comes through that little hole, which is where the electrons are being generated. So the electrons are being generated, these things has to be generated, and it goes down to the chamber, which is controlled by a magnetic field, and hits your sample, goes off the detector. There's one detector, there's two detectors. The sample itself has to be coated either in gold or palladium to conduct the electron beam. Also, the sample has to be hard enough, well, made solid. So if you're using a tissue sample, you have to either freeze dry it in some sort of way to get it hard, which we have a critical point freeze dryer, or you could use liquid nitrogen. You may be able to get away with it, but mostly if you have a hard material, you really don't need to freeze it or anything like that. It could go in it. But the samples have to be hard to conduct so that the vacuum system won't crush it. And you want the samples to be as lifelike as possible. So when you're doing it,
Lifelike as possible?
lifelike as possible.
What do you mean by that?
Okay. You want it to okay, I should say vintage original state.
Okay.
So if you're looking at an insect, you don't want it to look dead. You want it to look like, or have the same compositions. For example, this is Jack Spanner here, which I coated
In gold or palladium?
in gold. So it still has its original state where it was, you know, these are like flies. Right?
Yes, let me get
Lies and Jack Spaniards.
But you want to keep everything into its original state, because especially with tissue samples, the minute the blood or whatever gets out of them, they tend to squash and disintegrate. So you want it to stay in its original state. All right. Any questions so far?
Yeah, this fly is still green. That
Yeah.
one wasn't painted with the green screen?
Actually, just the top one was coated.
Okay.
I tried to keep it, you know, it's one of those hard beetles, so I tried to see how it looks original without coating it, and that's. All right. So, to give you an idea of what you're looking at there, well, I'm taking the images, what comes up here, I'm just transferring it here to our screen to digitize online images and stuff. We used to use Polaroids in the past, but they're non-existent anymore. So, all right, so this is ant. And what I'm going to look at is just the eye of it. So you can see the detail. And all I'm doing is just raising the magnification. And you can see detail about it. So I can keep going up into where you can see whatever detail you're looking at. Depends on what you were looking at as far as the eye is concerned. But that's just one part of it. So let me show you some of the samples we look at. So let me start with this one. This is a red palmite. Now this was colorized with using Photoshop, but this is a red palmite which you find mostly around coconut trees, the coconut branch turn brown. So you have these mites that usually is the cause of it. This is bacteria. These are animals. Just to show you what bacteria looks like. It's more cling on to the mucuses and stuff. This is the same ant I'm looking at. This is the jaws of it. This is like a batrack. It usually cuts some trees and stuff. This is an ant with the jaws closed. This is a fossil, which is about 60 million years old. It usually found around oil wells. This is from engineering, actually. These are fossils. This is beetle, fly. Cross section of a tree stem. This is a pea pod from weevil pod, actually. Fossil. These are eyes of a fly. Lava. Yeah, questions?
Yeah, around the eyes of the ant and the fly, I noticed there's this little white specks. What are those?
Dirt.
Just dirt?
Yeah. What when or these you
Yeah.
talking about? Yeah. Some could be dirt. Some could be things. You know, you can magnify it to make sure what it is. But most of your samples, you try to clean off as much as stuff as possible and don't make it any kind of foreign materials, because you will have questions like that. What is it?
Yes.
Lava. This is a cross section of a coconut branch. Now, may I ask why you want a cross section of coconut branch? Some of the students, this was actually done in physics. They were making a handle for a cricket bat, and they were looking at different types of wood. And this is coconut branch they were looking at for the sponginess of it, and where they were looking for something much harder. So they were looking at different types of wood to make the handle for a cricket bat.
So it's to look at the structure of.
Yeah, it's more as I say research. So they look at different things to see what's best for them. This is a cross section of the tree stem. This is the sperm of a goatee. This is a macaroni, and this is a weevil. I think you're familiar with that, but it's a weevil. But again, what I'm trying to make it as lifelike as possible, because it's dead, but
So you will place the weevil with some macaroni.
Well, I had the macaroni and then I stuck the weevil on top of it.
Oh, okay.
And then, yeah, so that but this has to be freeze dried also to make it, So this is fossils. This is a black beetle. If you're familiar with a black beetle, it's more plasticky at the back, but when we look close, it's furry. This is the eyes of a fly. This is the eyes of a mosquito. Now, this is a close-up of a mosquito eye. Now, again, you might want to ask, well, why are you looking at eyes of a mosquito? Now, if you look at this image of this screen, it's all full of little pixels, like receptors. Same as the mosquito, it uses these light receptors to form an image of whatever it's looking at. So, there, ladybug, fly. This is a body of a fly, and I'll show you how this is blown up to see the details of what's on the fly. There's a fly, eyes, body of a fly, fossil fly. This is what I'm saying, how it's blown up. Like this here, go back. Where is it? Past it. Right. So here is actually here. So that's the detail you can get looking at one strand of hair on the fly. Right. This is this is a macaroni, and this is the weevil inside the macaroni. So some people might say buy it like that. I don't know. This is a spider, and the spider's eyes are different because they're more mirrored. So they use 6 eyes.
That was a freeze-dried spider, or it was created?
Actually, I found this spider in here, and it was already dead in that same form, so I didn't have to freeze dry it.
Okay. It
So-
was solid enough to just go ahead.
Yeah, it was just like a turkey.
Okay.
Yeah. This is kidney stones. There's bacteria on it. This is what kidney stones look like.
Sure.
Yeah, see why it's so painful. So that goes through your bloodstream. These shells, seashells, fly. This is a male mosquito. And again, freeze drying it. I did not freeze dry it, so the vacuum just sunk the eyes in. This is a coconut branch with red palm mite. We have these eggs and stuff on it. Red palm mite, monkey branch. This is a mosquito, and these are the body of the mosquito. You can see the details on these wings and stuff. These are the eyes of the mosquito. Just float it up. The mosquito, these just body of it and showing the details so you can find out. This is a TM image of inside of a blood cell, actually kidneys. I'll show you the TM images in a minute. And this is a weevil, the same weevil on a macaroni. Fossils, the TM image, fossil, spider, fossil, is an ant, this is a spermatozoa, spider, the eyes of the spider. And on sugarcane, you see some of the sugarcane turn black. These are the spores that are responsible for it. These are the spores that on the sugarcane. The fossil, and that's adultic. So that's just giving you an idea of some of the stuff we do here. Now, you're in physics, so I guess you would be looking at materials more or less. So what we have is a detector, a UDS detector, and energy dispersive system, which we can actually, like my watch, I can tell you the type of material it's made out of through a spectrum analysis of it. This is a sample I'm looking at here. Actually, these grids are copper grids, which you're going to see when I talk about the 300 mesh grid. This is a 300 mesh grid that we're going to use on the TM. But for this purpose, what this sample is made out of is carbon, copper, and aluminum. And what I could do is put the electron beam on an area, and it will just give me aluminum peaks. If I put it on the copper area, I just get copper peaks. And it tells me the energy level of the copper peaks. You can identify which material it is, and the same here with carbon, which is giving me the carbon peaks.
What do you mean by the energy level?
It could tell me, well, what's the energy level of the secondary electrons that they're being kicked off. Right? And if you look at your periodic chart, it'll tell you the material and the energy level of it. So, and then it could go into small details of the different areas, like you can make a small area, small, whatever you really want. And then it could get actually a mapping of where my carbon is, where my copper is, where my aluminum is. So I could know, like on a material, which part is where. Real life situation, I had one of the doctors here were growing bones, and they were growing it on 3 different mediums: wood, plastic, metal. So they wanted to know what medium was growing the bones better, and I can give them like a mapping of the area of where how much calcium is being shown up, and how the bones are being created. That's for dentistry.
Which material would be best one?
That's their word.
Okay, that's confidential
Yeah.
information.
That's their word, because if I tell you, then you will say, oh yeah, this is the best one, and then
Okay.
somebody will like, well, how you...
I would assume it depends on
Yeah.
the type of metal.
Yeah, it depends on how you grade it and time and everything like that. You know, they go with time and temperature and all that kind of stuff. So it's their research, you know. But then too, I could give you percentages of, you know, how much percent, again, with the calcium or whatever. So that's the EDS detector part of it, and this is the imaging part of it. So, any questions?
This is which electron microscope?
Scanning electron microscope.
Scanning electron.
That's it.
Yeah.
Right?
Do you do any research here? Well,
No.
So you just scan?
Yeah, I do all the work.
Okay.
So I just don't do. All right. No more questions. I'll take you over to the TM. This is the grids I'm going to be talking about. Show you how the TM.